Hello. So in this video, I want to talk about an exercise in Folland chapter 1, section 3 about measure. Um, I think um, I'm really excited to work on this exercise because uh, based on my experience of study the subject in last year, I think it uses this exercise uses a technique that is very common. And first of like when I was first doing this type of problem, I have no clue, and I feel like the steps are very complicated. I always like look at my homework solution and I forgot about it. So since I am preparing for the qualified exam and I'm reviewing everything over again, I do want to master this technique. So let's get started. Okay, so let's look at the problem together. It is number 15, chapter 1. So given a measure mu, notice that we're not saying anything about the finiteness of this measure. So mu could be a finite measure, or it could be infinite measure, or it could be sigma finite measure. It could be anything. Okay, and then we define mu naught on M, where M is the sigma algebra. By mu naught E is equal to the supremum of mu F, where F is the subset of E, and the measure mu F is going to be smaller, strictly smaller than infinity. Okay, so we have defined a measure space, and we're given a measure mu. There's no restriction on mu yet. And we define mu naught measure, which is mu measure. Well, we sort of defining something that could potentially be a measure, but we need to prove that, right? So that is included in number 1, which is part A. Okay, so let's do part A together. And part A uses the technique that I mentioned at the beginning of this video. It uses approximation, and you will see later. So oftentimes in real analysis, especially in the section of measure theory, we want to prove some equality, right? And it's often hard to prove the equality directly. So a common technique is to prove both. For example, first prove smaller equal than, and then prove larger equal than. And usually smaller equal than, like one of the inequalities, very straightforward. But the other one oftentimes is kind of hard to detect. And this exercise gives me an opportunity to play around with one of the inequality and learn a very important technique. And hopefully I will be able to use this technique more flexibly in other problems. Okay, so for A, let's state our goal. So the first goal is to show mu naught is a measure. And the second one is to show that mu naught is a semi-finite measure. Okay, so let's do the proof of 1. Recall the definition of measure. There are 2 simple pieces. So first one is a measure of a thing is a measure. You can only if the first one is the measure of empty set is equal to 0. So we're going to check mu naught of empty set is equal to 0 holds since mu naught is equal to, by definition, is equal to supremum of mu f, where f is a subset of E, and mu f is finite. Okay, Um, and notice that because F is, so here is not E, I was just copying the definition. So this one here should be empty set. So because the only set that is a subset of empty set is, so that implies F is empty set, okay? And therefore, so this one implies this is equal to 0, and the supremum of a set of 0 is just equal to 0. And then we're done. And then this is the hard part. So let E j, where j is equal to 1 to infinity, in the sigma algebra M, such that it is disjoint. Okay, and we want to show that mu naught of the union of EJ is equal to mu naught of EJ. Okay, and if you look at the definition for mu naught, it involves with supremum, right? It looks complicated to show the equality directly. Like at least I don't have I don't have any idea about how to prove the equality directly. So what I'm going to do is I am trying to prove one of the equalities, right? Okay. Well, before that, we actually need to do some work because, okay, if we don't do that, just try to write down the definitions, right? So here, what we're trying to prove. This is supremum, of mu f, and f is a subset of union of EJ, and mu f is less than infinity. This is summation 1 infinity supremum of mu f, where f is subset of EJ, and so so the only difference here is f is a subset. So those are concerns about sets who are subset of the union of EJ, and those concerns about subset who is subset of EJ for every J. It's not clear to me like how to deal with that because this is really like a constraint, like the union is like a constraint. I don't think there's any theorem, or at least so far as I know, there's no direct theorem to pull this union outside as a summation. So how are we gonna do it? We're gonna digest them a little bit more before we going forward. So notice that the definition for mu naught involves with subset F, right? So every subset of F of this, and the measure of F is finite, and we're comparing the supremum over such F, and we pick the supremum, and that is mu naught E, or mu naught of union of EJ. Okay, so what we're going to do is let's so since we're taking supremum over subset of E such that a measure of that subset of E is finite, let's work on, or let's discuss more about that subset. So consider F that is in a union of one unity of EJ. Let's call this E, denote it E. Okay, consider this. Okay, and mu f is finite. Okay, so since EJs are disjoint. Since EJs are disjoint, that means since EJs are disjoint, that means F intersect EJ are disjoint. Let's make a new name for this. Let's call it FJ are disjoint. Okay. And so we choose a subset of E and we split the subset F into countable pieces. So it is a collection of disjoint sets. And what we know is that what else do we know is since mu f is finite, that implies mu of fj is finite for every j. Okay, so now we have a collection of disjoint set, and each element of that, collection is finite, has finite measure. What do we need? Why do we need that? Okay, so eventually we do want to show this, right? We want to show this. Well, what's the relationship between okay, let's think about this. Okay, so so first show this inequality. Okay, so we want to show this. Okay, how to show this? So let's write down the definitions. Okay, let's write down the definitions. And let's write this as E. So we want to show this, right? And write down the definitions. This is equal to supremum of mu of F, where F is a subset of E and the measure of F is finite. Okay, and so that's why we're concerning F here, right? So those F are potential candidates satisfy this. Okay, and since we want to show this inequality, notice that so notice if we can show, notice that if we can show mu of f is smaller or equal than this, which is smaller or equal than this, then the supremum, so supremum of mu f, where f Okay, let me write it. So if we can show this holds for all f that is a subset of E and the measure of f is finite, then claim 1 follows, right? So we just need to show that. And notice that mu f is equal to mu union of fj. Mu union of fj, because that is how we define fj, right? So you have a set, for example, you have set, and then you have a, for example, this is your set f. And what about and set f is inside of set E. Okay, and then you split E this way. So that is a countable union of E. So those are E. And then you look at this part. Now you look at this part. So this is one part, this is another part. So those are disjoint sets. And their union is equal to F, which is subset of E. Okay, so we have countable disjoint collection of sets, and then by definition of measure, countable additivity of measures is equal to summation 1 to infinity of mu of fj. Okay, why do we need that? Well, what's the relationship between fj and ej? Well, fj is a subset of ej, right? So let me see. It is true that each fj is a subset of ej because fj is equal to f intersect ej, sorry. But there's more we can say, I think. I am going to say this is smaller or equal than summation 1 to infinity. 1 to infinity mu fj mu 0 ej. Why? So I'm going to explain here. Since mu fj, since mu not ej is equal to the supremum of mu fj, such that fj is a subset of ej, and mu of fj is finite. Okay, so that is the definition for that. And so mu of fj is smaller or equal than mu of f, which is finite, right? So it satisfies this criteria. And what about the other one? So fj is definitely a subset of ej. So just to be clear, let me change my notation. So like those are not very good. Let's call it T. Tj, the subset of Ej, and Tj has finite measure. Okay, so and Fj, and since our Fj here is a subset of Ej, and we know that the measure of Fj is finite, so our Fj here actually our candidate over here. And because this is supremum over all of the candidate, that means this, okay, this one, which is one of the candidate, must be smaller equal than the supremum over all candidates. Okay, so and what is the supremum over all of the candidates of mu E, mu Fj? That is mu not Ej. Okay. And let's go back to our goal and see if we achieve, and I think so, right? Hence, mu f is smaller or equal than this, smaller than this for all f in E, mu f is smaller than infinity. Hence, the supremum, I just want to write it more complete, okay. F is finite, is smaller or equal than this, okay. And what is the supremum? Okay, that is mu naught E. Okay, I think I'm probably gonna do this one more time when I wake up, because I'm not sure if I can reproduce this. Okay, so so we're done with claim 1, right? So the next is claim 2. I'm gonna start in a new page. Okay, so claim 2 show that this is larger or equal than this. Okay. Well, how do we prove that? Show this is larger or equal than this. Well, case 1, which is a simple case, is that if mu naught of E is equal to infinity, then we're done, right? Because infinity, of course, is larger or equal than the right-hand side. Okay, so let's just do case 2. The case 2 is suppose that the mu naught E is finite. And we need to show the right-hand side holds, right? Okay. This is also like a regular pattern, like when we try to prove this, for example, this inequality, and then we find it's very hard. You think about the cases, right? The case, could it possibly be infinity? If it is infinity, then everything's easier. So maybe at least we can get 1 point from the exam, hopefully. Okay, so what do we have for now? So we need to consider the case that mu naught of E is finite. And what does that bring us to? So let's think about this. Okay, so first observation. So mu naught Ej are finite because mu naught Ej is less than mu naught of E, which is finite. Okay, why do we want mu naught Ej to be finite? Because mu naught Ej is finite. Okay, so let me just write it clearly. So mu naught of E, which is finite. Okay. And by definition, let's write down what it says, right? So by definition, it is equal to supremum of mu of fj, where fj is a subset of ej, and the measure of fj is finite. So we want to show this, right? And so observation, we need to show this supremum, this. Okay. And then we know this is finite. Because it is finite, that means this implies by the definition of supremum, right? So supremum is less than finite. Then we have there exists a specific subset fj, I think fj, that is a subset of ej, and then the measure of fj is smaller than infinity, such that supremum, which is mu naught ej, is smaller than measure of fj plus epsilon times 2 to the power of negative j. You will see why we choose that. Okay. And then what do we have? Or okay, this is equivalent as saying the measure of j is larger than the measure naught mu naught ej minus this. So we have this. And what do we have so far? So okay, now let's see. Now define Fn to be equal to the union I is equal to j. Let's do j is equal to 1 to n of fj. So let's define n to be this way. Okay. And what do we have? Since Fn is equal to this, since Fn is equal to this, we know that the mu of Fn is equal to mu of this union, right? And it is equal to, because fj's are disjoint, fj's are disjoint. So let's give it a special name. So there exists fj star such that j star j star. Okay, so let's okay, and continue here. Legal j is equal to 1 to n of mu of fj, right? And this is finite. Why? Because this is finite and this is finite. So together they're finite. So what am I doing so far? Like how am I doing? We're slowly going to our goal, although it might be not very clear what we're doing right now. So as you see, while we prove this less than finite, I think you might guess what we want to do next is fn. So also notice that Fn is a subset of what? Fn is a subset of Fn is a subset of Fn is a subset of E. Okay, so Fn, because Fn is, okay, I'm gonna circle this. So because Fn is a subset of E and the measure of Fn is finite, then that together they implies together they implies so recall, let's do a recall first. Recall that the measure not of E is equal to, I think I wrote it earlier. Yes, is this right? So suppose we have this, right? Okay. And notice that this is a supremum over all the candidates where each f is less than E and the measure of f is less than finite. So in particular, so this implies Fn, this implies Fn is less, sorry, so that implies the measure mu Fn is smaller or equal than mu naught of B. Okay. And then what do we know about Fn? Fn is equal to summation I to n of mu of Fj, right? Okay, so now we have what? So let's label. So we're gonna need some, we're gonna write down some inequalities, and then during the inequality, we're gonna need to use some result that we are used about. So we have mu naught E is large or equal than mu Fn, and this uses the inequality. Let's just call it 3. Okay, 3. What is this? This is equal to mu Fj 1 to n, which is equal to 1 to n mu of Fj. Right, and then what is this? Notice that mu of Fj is larger or equal than particular thing, so this is equal to 1 to n of mu naught Ej minus epsilon times 2 to the negative Ej. And this is equal to 1 to n mu naught Ej minus epsilon times 1 to n, 2 to the power of negative j. And I want to emphasize here, so we're gonna prove it, and then once we prove it, we are going to use it directly in the future. So notice that j is equal to 0 to infinity, 1 over 2 to the power of j. By geometric series, this is equal to 1 over 1 minus 1 over 2, which is equal to 2. If I remember correctly. So let me double check really quick. So geometric series. Okay. It is equal to 1 minus, so here, yeah, it's equal to 1 minus 1, oh, 1 over 1 minus 1 over 2. Great, that's exactly what I wrote here. So this is equal to 2. And now notice that it start with 1. So this is equal to j is equal to 1 infinity 1 over 2 to the power of j is equal to, if I expand it, you might be realizing that 1 plus 1 over 2, 2 plus 1 over 2, 3 plus 1 over 2, 4 plus dot dot dot, right? And this is equal to 1 over 2 times 1 over 2, 0 plus 1 over 2, 1 plus dot dot dot. So that is equal to 1 over 2 times summation j is equal to 1 to infinity of 1 over 2j, which is equal to 1 over 2 times 2, which is equal to 1. So at the end, we obtain this. So this is equal to 1. So we are going to just remember and directly use this fact in the future videos. Okay, so this is equal to, oh, sorry. So what I proved is after taking the limit. So let's take the limit on both sides. So the limit as n goes to infinity of this, okay, is equal to the limit as n goes to infinity of this, okay, and so this one does not depend on n, so I'm just gonna copy it down. Okay, this is equal to the infinite series, which is equal to 1 to infinity mu naught j, and this, right, is equal to minus epsilon times 1, right? Okay, and I'm going to erase this. Okay, so I'm going to write here, change this to 1. Okay, so now take n goes to infinity. Okay, we obtain this result. And then now, so since you can, okay, so now take epsilon goes to 0, and then we obtain this. Okay, so wait a second. Something is wrong. Sorry. Okay, so we have this inequality as desired. Hence, we obtained equality, right? Okay, we obtained equality. And to show the second one, to show the semi-finite, it is immediate. So I'm going to say trivial, since in order to show something semi-finite, it boils down to show that given a measure that is infinite, since if the measure not mu not e is equal to infinity, that means the supremum mu of f is subset of e, mu of f is finite. This is equal to infinity, right? And and we want to show there is a subset E such that the measure of f is going to be finite. So all we need to show is need to argue this is not an empty set. There is something in it. The word. Okay, so how do you show this is not an empty set? Okay. Well, let's think about this. Well, if this is an empty set, then you're gonna get 0, right? But you got an infinity, which means that cannot happen, right? Um, mm, okay. See. So this is just one definition. So, so there exists F that is subset of E such that the measure F is finite. So remember the definition for semi-finite measure. You actually still need to prove that mu F is strictly larger than 0. So we actually assume, so that is equivalent with arguing that it is impossible to, like, we can, let's prove by contradiction. Okay, so I need to prove that there exists F such that. So this F is actually, so this F is the one from this set. So for all F in the set, satisfy this. So now I'm going to show that mu F is larger than 0. So suppose not. So i.e. prove there exists F plus there exists F from this set such that the measure is greater larger than 0. So suppose not, i.e. suppose all F in this related set. Notice that this is a set of mu F. What I'm really saying is F in the set where F is a set where it is a collection of subset of E and the finite measure. So that's what I'm referring to by pointing out this to the set. Okay, so that means all F in this has mu F is equal to 0. Okay, so That means because we want to show there exists such f in this collection that the measure of f is greater larger than 0, is greater than 0. So to prove contradiction, let's just or um, or you can prove using contrapositive. I think either one works. So you suppose that all of the f actually, so all of the f in this set has to measure 0. Then mu naught e is equal to supremum of 0, right? Which is equal to 0, which is not equal to infinity. Hence we're done. Okay, so let's do part B. Let's see what is part B saying. Part B. I think part B is fine. So if mu is semi-finite, then mu is equal to mu naught. Use exercise 14. Okay. So mu is equal to, okay, so let's say if mu e is finite, then mu naught e is equal to, again, I'm gonna just copy the definitions of mu naught e. So if mu naught e is finite, then mu naught, if mu e is finite, then mu naught e, so those two, sorry about that. So mu naught e is equal to this, and because e is a subset of e, and then the measure of e is finite, so this one is just equal to mu of e by monotonic measure, and we were done. So if mu of e is infinity, okay, then by exercise 14 for all c in for all c larger than 0, right? Okay. There exists f that is a subset of e such that mu of f is larger than 0 is sorry, is larger than c is larger than c and smaller than infinity. Okay, and you can actually improve this to be for all okay, there exists well, actually this is equivalent with showing, okay, sorry, I think I should have written a supremum. So this is equal to the supremum of this. So this equals supreme, so this is equal to infinity by the definition of supremum. So just remind you, recall that supremum of set En, is equal to, where x is equal to infinity. So the definition for supremum, let's just review the definition of a sequence. So first of all, it is an upper bound of your sequence, and second of all, if since the supreme is equal to infinity, so if there exists m that is smaller than and for all that is smaller than infinity, m is not an upper bound anymore. So it is not an upper bound anymore. Okay. So number 3. Sorry. So it is not an upper bound. So that means there exists f is in E with some finite measures, such that the mu of f is going to be larger than m, right? So larger than 0 because measure of is always larger than 0. Okay, so you see the equivalence here. And we're done with B. So part C, let's review this part C. Part C uses some smart technique that I thought I didn't get through in the beginning. So I'll tell you where I stopped when I was firstly solving this problem. Okay, so show there exists mu measure such that mu is equal to mu naught plus mu. Right? So by analyzing the situation a little bit, because here mu could be it could be any measure, right? And have to be semi-finite. So which means when E is equal to so of course when E, so if you have E such that the measure mu of E is finite, then that will just return here. So mu naught E is equal to E by definition of mu naught E, right? So in that case, I want mu to be equal to 0. Mu E is equal to 0 if E is finite. And if E is infinite, so mu E is infinite, then we don't necessarily have mu naught E is infinite. Sorry. Right. So that's the difference from part B. So in that case, mu naught E could be finite, but on the left-hand side, mu E is infinite. So to let the equation holds, we need to set mu E is equal to infinity. So that gives me like intuition how to set up my mu, right? So mu E is equal to infinity. If mu E is infinite and mu E is equal to 0, if mu E is finite. Okay. That there is a problem. So what will be the problem? I was show the definition that mu is a measure, right? Then we're done. So the first one, that mu empty set is equal to 0. That is totally fine. That holds trivially. But if I have a collection of disjoint, countable disjoint sets, EJ, for example, I want to, so I want to show that mu of the union of EJ is equal to summation mu of EJ. So I have some trouble there because, so if at least one of EJ in our collection has mu measure infinity, then it is actually okay, because on the left hand side, I know that mu, since mu of the union EJ has infinite measure, I know that mu of the union of EJ is infinite by definition of mu. And because, so on the right right hand side, so summation of mu of EJ, it is also infinity. Why? Because there is one EJ such that mu EJ is equal to infinity. And no matter what others are, like once you do summation and one of the term is infinity, the whole term is equal to infinity. Therefore, the equation holds. So mu of the union of EJ is equal to summation of mu of EJ. But the problem appears when I try to consider the case that all of the EJs are finite, because that doesn't work anymore, because the union of EJ, where each EJ has finite measure, the union of that may have infinite measure. So that is the problem. Because mu of the union of EJ is equal to summation of mu of EJ, right? And I know that mu of EJ is finite, but unless mu of EJ is strictly less than 1, I cannot guarantee that the summation J is equal to 1 to infinity of mu of EJ is finite. Therefore, I cannot actually guarantee you that the mu of the union of EJ is finite. So it could be infinite. And once it is infinite, mu of the union of EJ by definition is equal to infinity. Okay. But on the right hand side, since all of the EJs has finite mu measure, when you do so on the right hand side, you have summation J is equal to 1 all the way to infinity of mu of EJ. And since each EJ in the case that we're considering right now is it has finite mu measure, so by definition of new EJ is going to be 0. Therefore, you are doing infinite summation of zeros, which is 0. So on the left-hand side of your equation, you got infinity. On the right-hand side of the equation, you got 0. Therefore, it doesn't hold. So that's why my initial thought does not work. So I need to construct a new measure mu. So now consider mu. Consider, so mu of E is equal to 0 if E is is sigma finite, and it is equal to infinity if E is not sigma finite. Okay. Let's think about how to work this out, right? Okay. So of course we want to make sure it is a measure, but before that, let's see whether they satisfy that mu of E is equal to mu naught E plus mu of E. So consider the case 1 and 2, right? So if 1 happens, which means E is sigma finite, if E is sigma finite, so again, we consider when when mu of E is finite, okay, then mu of E is equal to mu naught of E plus 0, since finite since finite measure E implies that E is sigma finite. So since E is finite implies E is sigma finite. Yes, 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 that's correct. Okay, and then okay. So what about when mu of E is infinity? Okay. So let's think about this. Okay, so sorry, I paused the video to think more about this. Now I think I figured it out. So we were discussing the two cases, right? The mu is finite, and then we have this whole. So we have the desired thing pose, right? And then now we're considering mu E is equal to infinity. Notice that if E is sigma finite, right? Okay, then we have then actually mu E is equal to mu naught of E. Why? Why? Because if given that, because then, so given that E is sigma finite, then there exists, let's call it union of EJ, where J ranges from 1 to infinity, such that E is equal to the union, countable union, and the measure of EJ is finite. Okay, so right, and define. So eventually, what is mu naught of E? Mu naught of E is equal to supremum of f of mu of f, right? Where f is a subset of E, and mu of f is finite, right? So it is equal to this. Well, clearly, okay, clearly, so we are defining, let's see, f, let's define Tj is equal to, so T1 is equal to E1 and Tj is equal to the union 1 to J of EI. Okay, let's do this. Okay, so we want to define this for every J. Okay, and then notice what? So let's notice something. Mu naught E is equal to supremum of mu of f, where f is a subset and mu of f is finite. So notice that here, mu of Tj is finite because since each Ej is finite and we are yes, so each Ej is finite and they are disjoint. So I can label this disjoint. Okay, so and this is finite, and because this is finite, right. So and we know that. So eventually, what do I want? I want that this is equal to mu of e. What is mu of e? Let me write 1 to infinity of ej, which is equal to mu of e. Okay. So it's a little bit unclear, but I guess you can see my intuition. So here can be any subset of E, right? And here this is a subset of E, and we know that for any J is going to be still a subset of E, and it has finite measures. So those are all candidates of this F here. So, and when we're comparing those candidates, the supreme of them is going to be the one from 1 to infinity here. That is my intuition. So, therefore, so as this grow, as J grow, this will converges to the union, converges to this. And of course, while it converges, it actually converges going upwards because TJ is increasing circles. So let's just leave it here, and if we have time, we can go back to sort of the details. So what's my point? My point is that mu naught E is equal to mu E is equal to mu E plus 0 is equal to mu E plus mu, sorry, sorry, I got it backwards. So it should be mu E, mu 0 plus 0, mu 0 plus mu of E, and then the equality holds, right? Now, if E is not sigma finite, then mu E is equal to mu naught of E plus infinity is mu naught of E plus mu of E, and we're done, right? So now proof mu of E is equal to is a let's prove that mu of E mu is a measure. Okay. Well, mu of empty set clearly is a finite, so it is not finite, so it's 0. Okay, and let E1, E2 be in M. So we need to show mu union 1 to infinity of Ej is equal to summation 1 to infinity mu of Ej. Okay. Okay. Sorry, let's go back to proof. So we want to show that. How can we show it? I think should be fine because mu of union of EJ. Okay, let's consider, right? So if all EJ follows mu me follows EJ are sigma finite. Okay. Okay, so let's call this E. Okay, so if E is sigma finite, okay, then there exists a collection that's called Kj, such that E is equal to union of Kj, where the measure of Kj is finite. That actually also tells us that each EJ is sigma finite, right? So because you have E and you split your E using Kj, okay, and then now if you have a subset, for example, subset of EJ, of course, it like since EJ is equal to, let's use a different index. So S, okay. EJ is equal to the union of K S intercept EJ. Okay, so is finite measure and then the union equals to EJ and it's countable unit. Okay. Because EJ is sigma finite, so mu of EJ is equal to 0, right? Therefore, given that E is sigma finite, we also have that also mu of E is going to be 0. So 0. So mu of E is equal to 0 is equal to summation of 0 where j is equal to 1 to infinity, which is equal to summation j is equal to 1 to infinity of EJ. Okay. So if one of the EJs is not, I think so. Yes. So if at least one of EJ is not sigma finite, the whole thing is not sigma finite, then E is not sigma finite. So mu of E is equal to infinity, and so this one BJ is not sigma. So summation j is equal to 1 to infinity of mu of EJ is equal to infinity. Hence, mu of E is equal to summation j is equal to 1 to infinity mu of EJ. So we write down more clear way is equal to this, and then so in both cases we were done. I think there are some additional things I need to mention. Let me check. I think the only thing that I need to like mention is if EJ is not sigma finite, then E is not sigma finite. I think this is clear because if you think about E, the definition, like E is a union of EJ, right? And if E, I suppose, so given that EJ, there exists EJ such that it is not sigma finite, and I suppose E is sigma finite, then that means there is union of Ki such that E is union of Ki where the measure of Ki is finite. And since EJ is a subset of E, then EJ is actually equal to EJ intersect the union. EJ, because EJ is a subset of E, right? So EJ is equal to EJ intersect E, which is equal to EJ intersect the union of Ki, which is equal to the union of EJ intersect Ki. But since Ki are finite, that means the measure of EJ intersect the Ki is smaller or equal than the measure of Ki, which is finite. So therefore, that actually shows that EJ is sigma finite, which is a contradiction because we prove EJ is sigma. EJ is not sigma finite. I just realized that the thing that I just said is actually a contrapositive proof. Okay, so I think this is almost done. And let me double check the earlier thing that I stopped at and see if there's anything I want to add on. Okay, I do have something that I want to add on. So which is about this part. So after we define new here, we want to show that new satisfy our requirement, which is this this equality. So I want to add on that. In particular, when the measure of E is infinity and E is sigma finite, I want to show that this equality still holds. Okay. So if E is sigma finite, then we claim these two are equal because because E is sigma finite, so you can find the disjoint disjoint sets such that the union is equal to E and each set is finite. And then a little bit modification is that we can define Tj such that Tj is in this way. So the union of Tj is equal to the union of EJ, which is equal to the union of which is equal to EP, and then each TJ is finite because because this is a finite union. This is a finite union of finite measure, disjoint measure. Okay, and so we have this. Let me make it smaller. So we have this, right? And then notice that you can actually ignore any subset F, satisfy this requirement, but F is not equal to Tj. So you can actually, what I'm saying is that this is equivalent or equal to supremum of mu of Tj, where J is equivalent, because since Tj is increasing to E. And then you are looking for a supremum. So for example, and the monotonicity of measure. So you have that, then the result is the same. Of course, you discard some subset of E, but the result, because you're looking at supremum and the measure of Tj is increasing because Tj is increasing sequence of sets. So you have this, and notice that this, so as I said, this is an increasing sequence of sequence, right? And so the limit of mu of Tj as j goes to infinity is equal to the supremum, because it's increasing is if the supremum of the sequence is a union is is a real number, then this sequence converges to the because it's upper bounded by a real number. If the supremum is infinity, then we can say, okay, this sequence just goes to infinity. So overall, the limit is equal to the supremum of mu of Tj. Okay, so that means the supremum is equal to the limit as j goes to infinity of mu of Tj. And what is mu of Tj? So let's make it even smaller because we need one more line. Okay, one more line. So this is equal to the mu of union j is equal to 1 to infinity of Tj by continuity from below. And those two are the same. Those two are the same by our construction, and this is equal to E, and therefore this one holds. Okay, it's a long proof, and I think I wasted time, and I probably gonna try to prove it again tomorrow after I woke up, just to make sure I remember the tricks and be familiar with this. And thank you for watching, and always let me know if I made any mistakes. Thank you, and good night.